to begin with, there's a quote that we'd like to share that embodies a lot of the engineering spirit that comes out in our product in TypeDB. And that's this quote from Alfred North Whitehead, who said a long time ago, actually over 100 years ago, said that civilization advances by extending the number of important operations we can perform without thinking about them. And there's something very powerful about this quote, and especially in relation to computer science and programming languages specifically, which is the fact that we can create abstraction layers to push down effectively certain operations so we can work at a higher level, we can solve problems at a higher level, and ultimately push science, push civilization forward, whether that's because we can now solve certain diseases, we can build self-driving cars, or anything like that. But why did we start TypeDB in the first place? What's the problem that we saw when it came to actually the technology, that the technology can address itself? And we can answer that question by looking at an example data set. So now let's take a domain with a lot of different types of relations, and specifically a supply chain domain. Let's say we've got a product that needs to reach a certain destination. Now, if we have that, we may also have a lot of other variables that we want to take into account, whether it's delivery, whether it's trucks, availabilities, employees. And if we model the entire supply chain or a logistical network domain, there's a lot of other more variables that we also want to take into account. And if we're trying to model this into a database, the data model itself soon becomes too complex. And it's not too uncommon that the data set, the SQL queries that we have to write become so complex that they may end up looking like this. This is one example SQL query that's just over 150 lines of code. Now imagine debugging that if that doesn't run. And so the question then begs, what makes data complex? And there's a couple of things that we focus on here. The first is that of type hierarchies, specifically entity type hierarchies and relation type hierarchies. Let's say I've got different types of entities and I want to subtype them. For example, we've got an animal that may be subtypes that has subtypes such as mammals, reptiles, human, cats, crocodiles. But I may also have relation type hierarchies. For example, an employment relation that I may want to subdivide into temporary employments and permanent employments. And I also have a lot of different types of relations that I want to model. For example, unary, binary relations, but also and which we can subdivide into more different types of relations. We also have the need to model things like ternary, n-ary, and infinitary relations, but also nested relations, equivalent relations. In short, there's a lot of different types of relations that we want to natively model, natively represent in the database, because that's effectively how we consider the domain to be accurate. And that's how we also want the database to be able to model it. But then what makes querying those complex networks so challenging? Now, if we look at an example again from a logistical network, let's say we have a question such as which organizations have premises in the UK? Now, let's assume we have 3 different types of organizations: companies, charities, and universities. Let's say we have 3 different types of premises: offices, laboratories, and warehouses, and 3 different types of destinations: cities, wards, or countries. Now, in order to answer this question, effectively what we have to do is to write some sort of query that actually traverses or makes 3 to the power of 3 number of permutations in the actual query. So in terms of the actual traversal that we end up writing, is we end up with a query that is very permutative and also verbose. But why can't current databases handle this type of complexity? Now, the reason is simple. Firstly, when we look at SQL is too low level. It works at third normal form and killed by joins. If we look at graph databases, we also don't see any schema. There's no constraint. It's also too low level. And then finally, RDF and AL for those who come from that space. We also consider that to be too low level, verbose, and ultimately built for the web using open world assumptions and designed for logicians. So what we see is that current database languages are really too low level to handle complexity. And so the solution that we're proposing is TypeDB. Now, for those unfamiliar with TypeDB, there's a number of key components that make up TypeDB, or specifically TypeDB's type system, because that's the core central tenet of the technology. And the first part of that is the expressivity. The expressivity of the language allows us to model data accurately and in a representative way. The second is that safety, both in terms of data input and data output. The third part is the inferencing capabilities, being able to abstract away certain patterns into some sort of abstraction that we can then refer to. And finally is the optimization, being able to use all the information in the type system to actually optimize and help the query planner write better queries. And so those four components, the expressivity, the safety, the inference, and the optimization all together make up the type system in TypeDB. And the fundamental problem addressed by a type system is to ensure that programs have meaning. Because the more expressions and restrictions that are imposed by the type system, the more strongly typed a program is. So that's why the expressivity provides us with richer data structures. The safety provides us with meaningful input and output of data. The inference provides us logical abstractions of data. And finally, the optimization, it gives us efficient execution of queries. And that's why we say that TypeDB is a strongly typed database with TypeQL as its query language. Now, before we dive into each one of those components, I actually want to do a demo. I want to do a demo of something that we're about to release. Now, if you've worked with TypeDB, if you've at least looked at it, I'm sure you're familiar with Workbase. Now, we've actually built a replacement of Workbase. And this replacement is what we call TypeDB Studio. And I'm actually very excited to say that this is only the very second time that we're demoing TypeDB Workbase, because it's still under development. We will be releasing a beta version very, very soon. But currently, we redesigned this from the ground up, so the performance is much, much better than the current Workbase. So the demo data set that I want to show you is effectively a risk structure. And if you've attended any of these talks before, you probably would have seen this particular example. But what I want to show is how we can actually use the inference engine to effectively abstract away, to ask a high-level question and get an answer that's seemingly simple, but hides away a lot of the complexity under the hood. So the data set itself that I showed is a financial data set, like I said, with ownership structures, with risk score organizations. And the query that we're asking at the top here is asking for, give me a bank. So this is an entity type that we assign to this variable called $bank. We then say that there's an entity type risk score, which we assign to this variable named risk. That risk score has a risk level with the value high. And then we say that the bank and the risk are in a risk exposure relation. So the query is effectively asking us, give me banks that are exposed to high levels of risk. And the result below, the result that we see is basically there's a bank that's exposed to the civil unrest score. There's another bank, there's the same bank is also exposed to this war score. And similarly, this other bank is exposed to both the war score and the cybercrime score. All of those risk scores are connected to this particular risk level, which is a high risk level. Now, the beauty of this is that there's two types of inferencing going on here. So there's type inferencing, and the second is rule-based inferencing. But I first want to focus on the type inferencing, because this is something so subtle, but something so powerful when it comes to actually writing or simplify or creating an abstraction of the query, is that we're asking for we're asking for an entity type risk score, but the types that we're getting back are civil unrest, war, and cybercrime. And so, and while we didn't explicitly ask for those subtypes, we're still getting them. And that's because those three risk types are subtypes of a risk score. So instead of having to write a query where we ask for, give me a bank connected to a civil unrest type, a bank connected to a war type, and a bank connected to cyber type, I can now simply abstract away and simply say, give me all the risk score. So that's the first abstraction that we see here. The second one, which is perhaps more interesting from a narrative point of view, is that now these four relations right here, so these risk exposure relations, they don't exist in the database. So they're not persistent. None of that is actually persistent in the database. And they were created at query runtime when we ran the query. But as a user, so if you're connecting an application and programmatically talking to the database, it's as if they're persistent, but they're not persistent because they are inferred when we run the query. Now, because the inferencing is based on rules, on logic that we represent as part of the schema, we can actually ask TypeDB, why was that inference created? And in this case, we see that the reason for the inference here, that why is this bank connected to the cybercrime score? The reason is because it seems that this bank is under some sort of cyber attack that's connected to the cybercrime score. And this is where it gets even more interesting, because while this relation is actually persistent in the database, this one isn't. So it's actually not even that same bank that's under attack. It's actually a subsidiary, because if we drill down even further, we see that the actual bank that's under attack, or the actual entity, is this real estate corporate, which is a subsidiary of this particular bank. And actually, if we look further, it's not even a direct subsidiary, because it's a subsidiary of yet another subsidiary. And then if we look here, then this bank here is connected to the civil unrest. Why is that? And here, if we look one level deep, we see that that bank owns a particular energy asset that's in a jurisdiction that's connected to that civil unrest score. And finally, why is this bank connected to this? Why are two banks connected to exactly the same risk score? That's a fairly high coincidence, right? Now, the reason is that, and this is where it gets quite interesting, because now under the hood, first we can see that this bank owns this particular bond, which is issued in a certain jurisdiction. That jurisdiction is connected to this war score. But the ownership structure of that bond is the one that's interesting. So because this is yet another inferred relation, because if I go one level deeper, we see that this bond is actually owned not by this bank itself, but it's actually owned through a joint venture, this entity right here. So this entity is owned by these two banks. So these two banks have this joint venture, which is represented by this ternary relation. This is one example of the hyper relation in the TypeDB's data model, where we can represent three role players inside of one relation. You can't do that in a graph database, for example. And now if we look even further, now the joint venture actually doesn't even directly own that bond, because the way the exposure is built here is that actually this particular joint venture has a board of directors. That board of directors has one member, this man here, who's married to this woman, and that woman actually owns that bond. And if we go even further, we see that she doesn't even own a person. She actually owns it through a special purpose vehicle that, if you look deep in the data, it's Zurich, it's Geneva, or Geneva in Switzerland. And so the point is that, so we started with a very simple example, very simple answer to the question. The question was, what are banks that are risky? But the underlying explanation, or the abstracted explanation for why the result was given, which is effectively these two banks. This is what your application wants to know. This is effectively the answer to the question. This is what you care about when you're querying for the data. And so when we talk about abstracting away logic, when we talk about abstracting away complexity, this is that in the literal sense, because if we zoom out, this is already a fairly complex set of relations. So now if you've got any questions about that, please do post them in the chat, and or if it went too fast. But I'm very excited that this is the second time we're actually demoing TypeDB Studio, and we'll be making it available hopefully very soon. And do keep an eye out on Discord if you're interested to get your hands on TypeDB Studio. So going back to the presentation. So now what I want to do now is go through all the 4 key components that make up TypeDB. And so the first, as we saw, is that of the expressivity, because that's what we see in our community, what we see in all the people that love TypeDB and use the language to build their applications, is the ability to represent data more expressively in a simpler but yet very powerful way. And the core component of that, what enables all of that, is the fact that this is the type system, is the expressivity of the data model. Because the data model in TypeQL, how we implement it in code, is a direct implementation of the entity relationship model. That means we don't need to normalize our data. We don't have to impose whether it's a tabular structure on our data. We don't have to impose some sort of graph structure on our data. The entity relationship model is actually how we implement it in code. And what that means is that entities, attributes, and relations are all first-class citizens in the model. What that means in practice is that we can actually have attributes, which is a concept that is incredibly powerful for those who know how to use it. Or we can have nested relations, and then we have the concept of a role that contextualizes how something relates to a particular relation. And finally, we have rules that allow us to abstract away and do rule-based inferencing, and we'll get to that in a second. But first, let's look actually how a basic schema works in TypeDB. So the TypeDB schema, it sits and is modeled at first normal form. And we say that a relation is in first normal form if and only if the domain of each attribute contains only atomic values, and the value of each attribute contains only a single value from that domain. So let's say we're modeling a company that plays the role of an employer in an employment relation, where a person plays the role of employee. Both of them have names. So on the left, we have the visual representation of how that would look. And on the right, we've got how we would actually implement it in code. So like I said, the actual model from an entity relationship point of view is actually how we also implement it in code, which is what you see on the right. We've got a person, that's an entity. We have a company, that's an entity. We have an employment, that's a relation, and name, that's an attribute. And we use the keyword sub to indicate the fact that those are indeed those types. We use the keyword owns to connect an attribute to a particular type. And then we use the keyword place to indicate that this person plays the role of employee in an employment relation, and that relates then that role name, that role player, to that particular relation. And by the way, this is already roughly 70% of all the keywords in TypeDB. So if you can follow, if you can read this, you're already well on your way to actually getting a handle on reading TypeDB schemas and writing TypeDB schemas. Now let's say we want to extend the model, and we want to actually also create subtypes. We want to add a new type, a startup and a customer. To do that, I can simply say customer sub person or startup sub company. We add an additional attribute, rating or funding. But because they're subtypes, in this case, a customer is a subtype of a person, they inherit all of the roles and attributes that its parent has. So that's why we say that a subtype may inherit attribute or role types from its supertypes, and it may also overwrite them. Let's say we extend the model further. We say there's a marriage between a husband and a wife, and let's insert some data. So this is what we would write to actually insert data. We say, instead of saying define, we use the keyword insert to say that, hey, TypeDB, I want to insert some data instead of schema. And we want to say that IBM employs Alice. Alice is married to Bob, and Bob works at a startup, Kraken. Now, to do that, we first have the concept of a variable, which is denoted by this $sign. we say that this variable company, which is assigned to this entity type company, has name IBM. Alice has name Alice. And then we say that Alice and company are in an employment relation. We then also say that startup is connected to a customer in an employment relation. And Alice, which is a person, and Bob, who is a customer as well, are in a marriage relation. Now, again, note that we didn't explicitly allow customers to be employed by startups. But because startup inherit the ability to play the role of employers, that is allowed instead of having to explicitly define that. And then we've got all sorts of different types of relation that we can model. For example, reflexive relation. Let's say we have Alice who's teaching herself. We've got Alice who can play both the role of teacher as well as taught in a teacher's relation. We may have symmetric relations where Alice can play, where two different types can play the same role. In this case, in marriage, there may be two role players, two roles called spouse. Or ternary relations, where we've got one relation, in this case, a purchase relation between a product, a seller, and a buyer, all encapsulated in one relation to denote the fact that a purchase consists of those three role types. And again, we're not limited to just ternary relations. We can also create n-ary relations, where one relation can have effectively n number of things in that one relation. In this case, a joint venture may consist of a bunch of owners and one owned company. And then we also can have nested relations when one relation refers to another relation. The example here, we have a marriage between Alice and Bob. And let's say we want to localize the marriage. That marriage happened somewhere in the world, as long as it was physical. And let's say it happened in London. We can actually assign a variable name, $M, to the relation marriage. And we can now, I mean, I think this is really, really cool. We can literally put that relation in another relation. Now, what that means to your schema, that of course depends. But this is one of the many unique things about using TypeDB. So we say that the expressivity is that the type system enables programmers to think higher level as opposed to join tables, columns, vertices, edges, and properties. So now let's look at the safety aspect. So we saw these types here. So given these definitions, let's try and insert some data. So let's say, could we insert that a customer is married to a person? This is the same query that we saw before. And I already mentioned this, but the type that this commit would succeed because type validation would be able to infer that customer is a subtype of person. So we didn't have to declare customer being able to be connected to a person, but because customer inherits from person, that is allowed. But could we insert a person married to a company? Now, I must admit, especially here at Vertical, some people may want to marry their company, but that's of course not possible in the real world. And so in this case, this would not be allowed. So if we're trying to, this commit would fail. So the type validation would detect that there's no logical interpretation of the type definitions that allows a person and a company to marry. Unless, of course, you change the type definition, you change the schema, and you allow a company to marry a person. And by the way, that's another important thing that we can, and if we need to, we can indeed at any point in time during the database lifecycle change the schema at any point in time, as long as you're not writing data. Because when you do a schema commit, you can't. There's a lock during that period on any writes, but you don't need to do any expensive migrations, for example. And then how do we query? So for example, here we're querying for query. So let's say we have a model. Can we query for people owning cities? We can't. So type resolution would detect that the query is not satisfiable by the type definitions and throw an exception instead of returning an empty set. And this is very important because if you've got a very long query, a complex query that touches a lot of types, it's going to be a pain to actually debug that if you're not being returned the data that you're expecting. So that's why TypeDB checks whether there's a check that checks whether the query that you're asking, this is not during insert, this is during a match query, whether that match query actually adheres to the schema. So you know that the type system detects meaningless and invalid queries, resulting in data that you can trust. And then we move to the inferencing part. And this is what we were looking at during the demo, specifically the type-based inferencing and the rule-based inferencing. So how do we write rules in TypeDB? Now let's say that we want to infer that if London is in the UK, then the UK is also in Europe. Despite Brexit and all, the UK is still very much in Europe. And so if we find that in the data, we want to infer that London is therefore also in Europe, even though there may not be a direct relation between London and Europe. And that type of rule, that type of logic we can represent through a rule that looks like this. So given a set of conditions, and those conditions are expressed in a TypeQL pattern. So whatever you can express in a TypeQL pattern, we can also express it in a rule. That if that is true, at any point in time, whenever we query for the database, then TypeDB is going to infer some sort of new fact, some sort of new statement, an axiomatic TypeDB, TypeQL query or concept is going to be created. So whether it's an entity, an attribute, or a relation that you want to create, you can all do that in a rule like so. And another example, let's say that we've got a parent that has two children. Now, we can create a rule that says that if two children or two different people share the same parent, to then infer that they're actually in a siblingship relation between those two parents, or between those two children. Now, and of course, we can get much more complex when it comes to the conditions that we put in the rule. The point is that we can create, or we can effectively, in a rule-based way, infer new data on the fly. And if we go back to the example that we looked before, so which organizations have premises in the UK? So this seemingly small, but actually very verbose and complex query, we can simplify quite easily like so, where organization and premise use type inferencing to infer and to derive every subtype of organization, every subtype of premise. And then the rule inference allows us to determine all the possible locations in the UK. And if we take this to the extreme, and this is actually a query that is in the biomedical space, this 150 SQL line query, we can abstract that into just a couple of lines of code in TypeDB. So with type and rule inference, we say that complex and verbose data patterns get abstracted to their logical equivalent. And that's why the type system encodes the domain for logical interpretation by the reasoner, enables type inference and rule inference that creates logical abstractions of data. So in the last section, we want to look at the optimization. So let's say how should we execute the query of find me a person and the company that employs their spouse. So this query right here is a fairly simple question. But let's say that the query planner under the hood in TypeDB sees that there's 1 million instances of person, 60% of people are married, companies have on average 30 employees, and there's 10 instances of companies. The maximum traversals that are created in that case, we call that the search space, is 1 million. That means ultimately that there's 180 possible successful traversals, meaning that the search space or the efficiency of the results is less than 0.1%. But instead, what we want to use, we want to use the information from the type system to inform us that actually if we start the query at company instead of person, the efficiency of the search space is 60%. And that gives us a huge increase in performance. Now, of course, the real optimizer equation for this query is much more complex. because it would contain a lot more variables and equations that make up the actual way of how TypeDB works. And especially when it comes to queries that are so much more complex, the more type information restrictions there is in the system, the more the optimizer can prune the search space exponentially, leading to more effectively more powerful, more performant queries. And that's why the type system provides information for the query optimizer to determine the most efficient execution plan. So to bring everything together, we spoke about the expressivity in the type system. We spoke about the safety, the inferencing, and the optimization. All those things together make up what we call TypeDB's type system. Now, as a final note for today, effectively that's why we call TypeDB a strongly typed database with TypeQL as its query language. And so, and that's the end of that's all I wanted to share for today.